Hello, I'm Marco Vitali from University of Dundee, and I'm going to present the recent work we carried out on the numerical installation of open-ended files in SoftRock within the GPFEM framework. So, first of all, what is the aim of this research? We know that chalk is at a foundation depth for several monopiles foundations in the North Sea, and monopile foundations are the most widespread type of offshore foundations. Unfortunately, during this installation procedure, there have been multiple episodes of pile refusal, meaning the available instruments were not enough to install the pile using driving, which and then pile refusal means the pile is not inserted, and you can see on the left two images of the two tips of two piles buckling under compression. This causes the damage to the pile and an increase to the, or decrease to the shaft capacity since the pile is not properly installed. And then you have episodes of pile run, as you can see in this video, that you can have actual loss of pile, meaning the pile just gets self-installed or drops into the chalk under its own weight and is no longer serviceable because it just goes underwater. So, what are the two main questions? How to predict drivability for the pile and what pile size to use. So, what's the capacity of a pile that you have installed? Current regulation prescribe for the latter are ultimate shaft capacity or distance between 20 and 120 kPa depending on the chalk density. While additionally for the capacity, field data shows that a progressive increment in shaft capacity is achieved after installation or setup, and which then decreases as the pile is loaded again. So we are simulating the installation procedure. The system is quite complex to simulate because it's full of nonlinearities such as large displacements, contact dynamics between the pile and the material that couple hydromechanical behavior and the chalk behavior itself. So here we're solving large displacement using the particle finite element method. It's one of multiple continuum mechanics numerical methods, and it works this way. So you consider a standard finite element model with nodes and elements and a connectivity matrix. After simulation step is carried out, the nodes can move as would happen in any finite element model. However, if you have achieved large deformations, the entities or the boundary between multiple phases or multiple objects is identified using an alpha shape approach. If you're not familiar with the alpha shape, it's a convex hull with a search range to identify which particles belong to the body. And then from the nodes identified, a mesh is regenerated using Delaunay triangulation, and the process starts anew. Then contact dynamics and coupled mechanical behavior. I'm not going into details, but we are using the GPFEM, which is an open source platform especially developed to solve geotechnical problems. And in this platform, the problem contact dynamics and coupled hydromechanical have been already solved by other people, as shown in the reference there. And finally, the material behavior. Chalk has quite a complex mechanical behavior because it behaves in a brittle way at low pressures, plastic failure when confined. It crashes into a putty, which is well, basically the constitutive material of the chalk itself, which was formed by the biological debris bonded together by the calcite. So here in this paper, we are representing the material behavior using a modified Clay model. You can see here this model expressed in stress invariant space PQ is characterized by two hardening variables, which are PT and PS. PT is the entity of the tensile strength of the material, so it can be calibrated from by Brazilian tests, and PS, which is the what will be typically the size of the surface in any isotropic hardening model. You can see on the bottom left that PT, so the strength of the bond of the material changes and can only decrease with the plastic deformation for both volumetric here on the left and for deviatoric, while the side yield of the yield surface PS itself can change depending on the volumetric deformation. So positive volumetric deformation, which means increases in volume, decrease the value of PS, and vice versa. So if you have dilation, the material will be plastic for, or it will be perfectly elastic for a shorter interval of stress, and vice versa, while the deviatoric portion only increases it. And this combination of softening and hardening can be used to reproduce the behavior of the chalk. Here we are using a combination of literature data and element testing samples to calibrate this model. As you can see here, the element tests were carried out on material from the location of St. Nicholas away, and you can see here on the bottom, we also have the link to a paper where I explain how this model was calibrated using a softetometer. Then after the model was calibrated, we used it to carry out some CPT tests. So cone penetration testing, you see here on the left, the contour of pore water pressure and or variation pore water pressure, and PT, so the bonded material, which is not reversible, so basically the rock damage. And on the right, you can see how the cone capacity and excess water pressure, the cone tip or the cone base change with the penetration, and you can see that they fit quite well for CPT test carried out in the same location, so South S and W for the investigated penetration depths. Okay, then we decided to carry out the installation itself. Here on the left you can see the model. It's an axisymmetric model, and it used to reproduce the test from the Alpaca and Alpaca Plus projects in the Wikinger offshore farm near Germany. The main characteristics of this model is that the pile diameter is set to 1.37 meters and the wall thickness of the pile is 40 millimeters. The pile itself is installed in a purely jacked installation, so controlled velocity, however, and not driven. However, this installation is fast enough, so we're calculating the the velocity or the hydraulic velocity, so that you can obtain driving lies excess pore water pressure accumulation. So this is the model. We installed considering drained condition and a partially drained condition. On the left you can see the very partially drained with a significant stress and the cracking propagating at the bottom of the pile. And after some penetration, you can see that the pile plugs and the plug is inserted with the pile, while on the right you have perfect decorative condition and the material dilates rising up to the pile. So if you measure the forces acting on the pile from the rain, you can see on the right you have force inside, force outside on the shaft, and tip resistance, so QB and QS. And as you can see, this value keep changing. They're not constant values, and since this mechanism keeps, or the ratio of internal to external forces or shaft capacity keeps changing, we assume this is due to a stake-slip mechanism. What does it mean? So a stake-slip mechanism means that the material gets stuck to the edge of the pile, and then a force keeps increasing between the material and the pile until the force is high enough that the material moves quickly and just slips inside the pile, causing an inversion in the ratio of internal to external shaft friction. So if we define the specific recovery ratio as the increment in material inside the pile to the increment of penetration depth of the pile, you can have two conditions, coring and plugging. In coring, you can see that the recovery ratio is equal to 1, meaning well, all the material that enters the pile just flows through it, and it's greater than 1 due to dilation, while recovery ratio less than 1 means the pile displays material at the bottom and it's not going to the pile. As you can see here, it's more visible for the drained case since you have actual plugging, and you can see that the inversion in the ratios corresponds to changes in the specific recovery ratio. By carrying out some cross correlation between the two, you can see that there is a correlation between shaft resistance and filling ratio for both. The two time series exhibit similar cross correlation ratios, so 0.6 and a lag of approximately 20 centimeters. The main issue with this method is that the latency is correctly coupled with the specific recovery ratio, which means that what we see as specific recovery ratio is not exactly indicative of plugging and coring behavior, since there is some delay and some smoothing due to the dilation. Then the other component we're interested in is pile durability. Buckley et al. 2021 provided this formula that correlates the cone resistance obtained from CPT data to expected radial stress during driving. And so this formula says that the radial stress profile along the pile is a function of the cone capacity during installation of CPT, the distance, the normalized distance from the pile tip, and two fitting parameters. One is the stress reduction factor between tip and shaft, which is typically assumed to be roughly 0.06, depending on the contact friction between the cone and the shaft, and a stress distribution parameter, which depends on the pile geometry. And Buckley et al. Defined it as equal to 0.77 for the pile type investigated here, and it's just a power function of the diameter to wall thickness ratio. So what do our numerical results show? The results seem to fit quite well, or the distribution of stresses fit quite well with the field data by Buckley et al. And despite being calibrated on a different data set, meaning this relationship can be used for different field data or scenarios. However, we slightly underestimate the effect of distance from the pile tip, as shown in the table, which could probably be explained by the fact that we are investigating an overall limited penetration depth, and the data where the fitting seems to be more or less similar to that found in the field. And finally, we assess pile capacity considering three scenarios. First scenario, we consider the capacity on tensile and compressive immediately after installation, so what's called end of driving with significant pore water pressure inside the material. A second scenario of long-term water pressure dissipation, and the third scenario where pile rusting and corrosion has increased the friction between the pile and the material. So what can we say? That between the two first cases, the tensile capacity roughly doubles with pore water pressure dissipation, which is consistent with literature data. It's possible to capture the shaft capacity increment to 300% from the end of driving state. However, to do this, we had to fudge the data and use non-physical excessive contact friction coefficients, which means a more realistic friction coefficient such as 35 degrees is not enough, and therefore it's necessary to consider different additional phenomena to explain the increment in pile capacity. So, conclusions: despite the very simplistic assumption we adopted, the model was able to capture quantitatively some of the available field data, such as normalized radial stress distribution and capacity increase following pore water pressure dissipation. This pore water pressure dissipation and the corrosion by itself is not enough to explain the significant pile capacity after setup. The measure and assumed ratio of internal shaft resistances are very different from those reported in the literature, and this could be due to the fact that we carried out jacked installation, while typically in literature people do, at least for larger scale piles, do driven installation. And this ratio could be used, or at least the numerical model could be used to investigate the stick slip pile response in order to identify what, for example, installation velocity or type of installation would be more beneficial. Thank you.